All right, let's just jump right into it. Have you ever wondered how these massive websites, think Amazon, Netflix, Google, can handle millions of us all at the same time without just collapsing? It's pretty amazing, right? Well, today we're going to pull back the curtain on the core ideas that make systems truly scalable. This is the secret sauce that keeps the internet running smoothly, even when it's under a ton of pressure. You know the feeling. A huge new product drops, tickets for a massive concert go on sale, and bam, the website is down. It is so frustrating. But it brings up a really great question. Why does being successful sometimes lead to total failure? What is actually happening behind the scenes that makes a super popular service just break? So, the root of it all is what I like to call the strain of success. I mean, it's a great problem to have when your service becomes incredibly popular, but it is a problem. The system you built, the one that worked perfectly for 1,000 users, just starts to buckle and creak when 1 million people show up at the door. And this strain, it breaks down into some very specific technical challenges. We're talking about a flood of requests hitting you every single second. You've got the risk of one server getting all the work, we call that a hotspot, and just getting completely overloaded. And of course, you absolutely have to stay online, even when a machine inevitably fails. The real goal here is to grow smoothly, predictably, not just, chaotically. Okay, so how do we deal with that first problem? Just the sheer number of people trying to get in. Well, this brings us to the first hero of our story today, a tool that is specifically designed to manage that incoming flood of traffic. It's called a load balancer, and its job is actually, in concept, pretty simple. The best way to think about it is as the internet's traffic cop. So instead of letting every single car try to jam onto one road, the cop is there, directing cars down multiple different routes. This keeps the flow smooth and makes sure no single road turns into a total parking lot. And here's what that looks like, basically. All the user requests, what we're calling clients here, they all show up at the load balancer first, so they're not hitting your servers directly. The load balancer acts like a smart gatekeeper, and it decides, okay, which server, S1, S2, or S3, is the least busy and best equipped to handle this request right now. So why does this matter so much? Well, first, it stops any single server from becoming a bottleneck, and that's huge. It also lets you do something called horizontal scaling, which is really just a fancy way of saying you can just keep adding more servers as you get more popular. And maybe most critically, if server 2 suddenly dies, the load balancer sees that and just stops sending traffic to it. The user on the other end, they probably never even noticed a thing. All right, so we've kind of solved the traffic problem. Our app servers can handle tons of requests. But in system design, as soon as you fix one bottleneck, you usually just find the next one. And this new challenge, it's all about the data itself. Think about it. Even if you have 100 servers handling requests, if every single one of them has to talk to one single database to read or write information, you haven't really solved the problem, have you? That one database is now your new single point of failure. It's got real physical limits, CPU, disk speed, and eventually it's just going to grind to a halt. And that brings us to our second big solution. This one is all about being really clever with how we store our data and how we find it again. We just can't use one giant filing cabinet anymore. We need a way smarter system. And that system really comes down to two key ideas. The first idea is called sharding. The best analogy I've heard for this is organizing a massive library. Instead of having one giant, chaotic room with every single book ever written, you'd split it into sections, right? Fiction over here, history over there, science in the back. Each one of those sections is basically a shard. It makes the entire system so much more manageable and way faster to search through. The upsides here are enormous. You can scale up your data storage just by adding more shards. It's that simple. Performance gets a huge boost because you can read and write from multiple shards all at the same time. And, just like with our servers before, if the history section has some kind of problem, well, the people looking for fiction books aren't affected at all. And that is the million-dollar question, isn't it? Okay, so we've split our data into all these different pieces. Now, when a user comes along and asks for their data, how on earth does the system know exactly which shard to look in? We need a really reliable address book for our data. So let's look at the old way versus the new way. The old approach, well, it was clumsy. It used a simple math formula, but the problem was if you added 10 servers and you added an 11th, that little formula would force you to reshuffle almost all your data. It was absolute chaos. The new way, consistent hashing, is so much more elegant. Imagine mapping both your servers and your data keys onto a big circle, or a ring. Now, to find where a piece of data lives, you just walk around the ring until you hit the next server. The beauty is, when you add or remove a server, it only affects its immediate neighbors on that ring. It's a tiny, contained change, not a massive disruption. And that's why this is absolutely critical for modern systems that need to grow and shrink all the time. This smart address book makes sure that scaling up or down is a smooth, predictable process, not some catastrophic event that brings everything down. This is really the key to elastic, resilient data. Okay, so we've looked at all the individual pieces. We've got our load balancer, we've got our sharded data. Now let's put it all together and see what the complete blueprint for a scalable system actually looks like. This flow right here perfectly sums up the whole journey. A user's request comes in, and it first hits the load balancer. That sends it to an available app server. That server then uses consistent hashing, our shard resolver, to figure out which specific data shard holds the info it needs. See? Every single step is designed to spread out the work and find data as fast as possible. But, and this is super important to remember, in engineering, there is no such thing as a free lunch. Every single choice you make is a trade-off. Load balancing is amazing for scaling, but you have to have really good systems for checking if your servers are actually healthy. And while sharding lets you scale to incredible sizes, trying to ask a question that needs data from multiple shards at once, like, say, what were our total sales across all regions, that can get very, very complicated. It's a powerful tool, but it's not a magic bullet. So we've walked through the theory, we've seen the diagrams, and we get the trade-offs. But the absolute best way to make these ideas really stick is to just apply them yourself. So seriously, grab a piece of paper or open up a whiteboard app, actually draw it out. Sketch a load balancer talking to 3 servers. Pick some imaginary data, like a user ID, and figure out where it would live on a consistent hashing ring. Think about how you'd shard your data. Would you do it by user or by region? The real magic happens when you try to explain why your choices work. That's what really cements the knowledge. And I want to leave you with this piece of advice because it's fantastic. It is so easy to get carried away and try to build a system for Google's scale when you only have 100 users. The real art is to build what you need for today, but to make smart choices, like using these patterns we talked about, that make sure you have a clear path to handle the success that's coming tomorrow. So the question is, what are you going to